In both 480 volts and 208 volt systems, the neutral conductor is indeed considered the current carrying conductor. Let's delve into why this is the case. Firstly, in a 480 volt system, we have a phase-to-phase voltage of 480 volts. This means that the voltage measured between any two of the three phases is 480 volts. However, the phase-to-neutral voltage, that is, the voltage measured between any one of the three phases and the neutral conductor, is 277 volts. Secondly, in a 208 volt system, the phase-to-phase voltage is 208 volts. Similarly, the phase-to-neutral voltage in this system is 120 volts. Now, the key reason the neutral is considered current carrying lies in its function within these systems. The neutral conductor is responsible for carrying the unbalanced current between the three phases. This unbalanced current arises primarily from two sources: firstly, unequal loads on each phase, and secondly, nonlinear loads that draw current in a non-sinusoidal waveform. Let's consider the scenario of unequal loads. In a perfectly balanced three-phase system, each of the three phases would carry an equal amount of current. The currents would be 120 degrees apart in phase, and the neutral current would theoretically be zero. However, in reality, electrical systems are rarely perfectly balanced. Different loads, such as lighting, motors, and appliances, are often connected to different phases. This results in unequal current draw on each phase. The neutral conductor then acts as the return path for this unbalanced current, carrying it back to the source. Without the neutral, the phase voltages would become distorted, potentially leading to equipment malfunction or damage. Secondly, nonlinear loads introduce another layer of complexity. Nonlinear loads are devices that draw current in a non-sinusoidal manner. Examples of nonlinear loads include electronic devices with switching power supplies, variable frequency drives, and some types of lighting. These loads generate harmonic currents, which are currents at frequencies that are multiples of the fundamental frequency, typically 60 Hz in the United States. Harmonic currents can cause a variety of problems in electrical systems, including increased heating of conductors and transformers, voltage distortion, and interference with sensitive electronic equipment. The neutral conductor plays a crucial role in mitigating the effects of harmonic currents. In a three-phase system, the third harmonic currents and other odd triplet harmonics multiples of 3 do not cancel out in the neutral conductor. Instead, they add arithmetically. This means that the neutral conductor can carry a significant amount of harmonic current, even if the fundamental load is relatively balanced. Therefore, it is essential to properly size the neutral conductor to accommodate the potential harmonic currents. Several factors influence the amount of current the neutral conductor carries. These include, firstly, the degree of load imbalance, secondly, the types and amount of nonlinear loads present, thirdly, the system voltage and impedance, and fourthly, the wiring configuration. To accurately determine the neutral current, it is often necessary to perform a load analysis and harmonic study. This involves measuring the currents on each phase and analyzing the harmonic content. Based on the results, the neutral conductor can be sized appropriately to ensure safe and reliable operation of the electrical system. There are specific requirements and recommendations for sizing the neutral conductor in electrical codes and standards, such as the National Electrical Code (NEC). The NEC provides guidelines for determining the minimum size of the neutral conductor based on the expected load and harmonic content. For example, NEC Section 220.61 addresses the sizing of the neutral conductor for household ranges and cooking appliances. It specifies that the neutral demand factor shall be 70% of the range demand of the unrounded conductors. This recognizes that household ranges typically have a balanced load, and the neutral conductor does not need to be sized to carry the full load current. NEC Section 220.20 through 220.61 provides guidance on calculating feeder and service neutral loads. Understanding these guidelines is crucial for electrical engineers and electricians to ensure the safety and reliability of electrical installations. Failing to properly size the neutral conductor can have serious consequences. An undersized neutral conductor can overheat, potentially leading to insulation damage, fire hazards, and equipment failure. In addition, excessive neutral current can cause voltage distortion and interference with sensitive electronic equipment. Therefore, it is essential to carefully consider the potential load imbalance and harmonic content when sizing the neutral conductor. In some cases, it may be necessary to upsize the neutral conductor to ensure adequate capacity. Another important consideration is the type of wiring method used. Different wiring methods have different ampacity ratings for conductors. The ampacity rating is the maximum current a conductor can carry continuously under specified conditions without exceeding its temperature rating. The NEC provides ampacity tables that list the ampacity ratings for various types of conductors and wiring methods. It is essential to select a wiring method that is appropriate for the expected load and ambient temperature. The ampacity of the neutral conductor must also be considered, especially in situations where the neutral carries a significant amount of harmonic current. In addition to sizing the neutral conductor appropriately, it is also important to ensure that it is properly grounded. Grounding provides a low impedance path for fault currents to flow back to the source, helping to protect against electric shock and equipment damage. The NEC specifies grounding requirements for electrical systems, including the size and type of grounding conductors. It is essential to follow these requirements to ensure the safety and reliability of the electrical system. The grounding electrode conductor connects the neutral conductor to a grounding electrode, such as a ground rod or a metal water pipe. This provides a direct connection to earth, helping to stabilize the voltage and provide a path for fault currents. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. In summary, the neutral conductor in both 480 volts and 208 volt systems is considered a current carrying conductor due to its role in carrying unbalanced currents and harmonic currents. The amount of current a neutral conductor carries depends on the degree of load imbalance, the types and amount of nonlinear loads present, the system voltage and impedance, and the wiring configuration. It is essential to properly size the neutral conductor and ensure that it is properly grounded to ensure the safety and reliability of the electrical system. Electrical codes and standards, such as the NEC, provide guidelines for sizing the neutral conductor and grounding conductors. Adhering to these guidelines is crucial for electrical engineers and electricians to ensure the safe and reliable operation of electrical installations. In addition to the above considerations, it is also important to be aware of the potential for circulating currents in the neutral conductor. Circulating currents can occur in systems with multiple grounding points. These currents can flow through the neutral conductor and other conductive paths, causing increased heating and potential for equipment damage. To minimize the risk of circulating currents, it is important to use a single-point grounding system. In a single-point grounding system, the neutral conductor is grounded at only one point. This prevents circulating currents from flowing through the neutral conductor. The NEC provides guidelines for implementing single-point grounding systems. Another important consideration is the use of shielded cables. Shielded cables can help to reduce the amount of electromagnetic interference (EMI) generated by electrical systems. EMI can interfere with sensitive electronic equipment, causing malfunction or damage. Shielded cables have a metallic shield that surrounds the conductors. This shield helps to block EMI from escaping the cable. The shield is typically grounded to provide a path for the EMI to flow back to the source. The use of shielded cables can be particularly important in environments with sensitive electronic equipment, such as hospitals and data centers. In addition to shielded cables, filters can also be used to reduce EMI. Filters are electronic devices that block unwanted frequencies. Filters can be installed at the source of the EMI or at the affected equipment. There are various types of filters available, each designed to block specific frequencies. The selection of the appropriate filter depends on the specific application and the frequencies that need to be blocked. Power quality is another important consideration in electrical systems. Power quality refers to the characteristics of the voltage and current waveforms. Poor power quality can cause a variety of problems, including equipment malfunction, increased energy consumption, and reduced equipment life. There are various factors that can contribute to poor power quality, including harmonic currents, voltage sags, voltage swells, and transients. Harmonic currents, as discussed earlier, can cause voltage distortion and increased heating of conductors and transformers. Voltage sags are temporary reductions in voltage. Voltage swells are temporary increases in voltage. Transients are short-duration, high-amplitude voltage spikes. Power quality monitoring equipment can be used to measure the voltage and current waveforms and identify power quality problems. Power quality monitoring equipment can also be used to track power consumption and identify energy-saving opportunities. Power factor correction is another important aspect of power quality. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is not being used to perform useful work. A low power factor can result in increased energy consumption and reduced equipment capacity. Power factor correction equipment can be used to improve the power factor. Power factor correction equipment typically consists of capacitors that are connected to the electrical system. The capacitors provide reactive power, which helps to offset the reactive power drawn by inductive loads, such as motors. Improving the power factor can reduce energy consumption, increase equipment capacity, and improve voltage regulation. Regular maintenance is essential for ensuring the safe and reliable operation of electrical systems. Regular maintenance should include inspecting conductors for damage, tightening connections, cleaning equipment, and testing grounding systems. A qualified electrician should perform regular maintenance. The frequency of maintenance depends on the type of equipment and the operating environment. In harsh environments, more frequent maintenance may be required. Proper documentation is also important for electrical systems. Documentation should include as-built drawings, equipment specifications, maintenance records, and test reports. Proper documentation can help to troubleshoot problems, plan for upgrades, and ensure compliance with safety regulations. Electrical safety is paramount. Always follow safe work practices when working on electrical systems. De-energize equipment before working on it. Use personal protective equipment (PPE) such as gloves, safety glasses, and insulated tools. Never work alone. Be aware of the potential hazards of electricity and take steps to mitigate those hazards. Electrical codes and standards provide guidance on electrical safety. It is essential to follow these codes and standards to ensure the safety of workers and the public. The Occupational Safety and Health Administration (OSHA) also has regulations regarding electrical safety. OSHA regulations are designed to protect workers from electrical hazards. Electrical systems are complex and require specialized knowledge and skills. It is essential to hire qualified electrical engineers and electricians to design, install, and maintain electrical systems. Qualified electrical engineers and electricians have the training, experience, and knowledge necessary to ensure the safe and reliable operation of electrical systems. Continuing education is also important for electrical engineers and electricians. Continuing education helps to keep electrical engineers and electricians up to date on the latest technologies and best practices. Electrical codes and standards are constantly evolving. Continuing education ensures that electrical engineers and electricians are aware of the latest changes to these codes and standards. In conclusion, understanding the role of the neutral conductor in 480 volts and 208 volt systems is crucial for electrical engineers and electricians. The neutral conductor is a current carrying conductor and must be properly sized and grounded to ensure the safety and reliability of electrical systems. Proper maintenance, documentation, and adherence to electrical codes and standards are also essential. By following these best practices, electrical engineers and electricians can help to ensure the safe and reliable operation of electrical systems.